Well, 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 look who's back. Yes, ladies and gentlemen, welcome back to a new video. It's been at least a few days, and this will be the last video of the year. But I do want to thank you all for being such a wonderful class, and it was a lot of fun. And just sorry that we didn't get to, meet again in actual school. But at least this was okay. Anyway, this video is going to be about linear regression inference procedures. So this was one of the topics that was cut out, and I just wanted to give you basically the main overarching ideas, and so none of like the nitty-gritty details, just the main concept. And then actually what I'm going to do is supplement this video with a video that was made by your peers on linear regression T intervals, and that video actually goes into some of the dirty work for me, such as checking conditions and all that stuff. So, and that's I do have to ask them, so there's no guarantee. I'm sure they'll be completely fine with it, but I haven't asked them yet, so that's a pending. But I'm almost positive they'll be fine with it. But of course, this video is brought to you by Couch Potato Brand Snack Food and Beverage. And as you can see here, I did a study on Couch Potato Brand Snack Food and Beverage. The more Couch Potato snack food and beverages that you ingest in grams, as you can see, there is a strong association with your happiness level. And we're measuring that by corner of the mouth height. And from now on, that'll be called CMH. So like, to get an idea of what I mean, let's say you're this person down here, that would be like me in the first grade picture that I think at this point many of you have seen. In fact, it's this same exact picture here. Unfortunately, right now the frown is covered with a mask, but that's this guy here. Very little amount of Couch Potato Brand Snack Food and Beverages ingested, and therefore very low happiness. This person here, I don't know, think the Joker from Batman. So that's the idea. You might notice, so yeah, strong linear relationship, positive, of course, but you might notice there are 4 outliers here. Actually, I don't want to rush to judgment, necessarily call them outliers, but they are definitely different points, probably influential points. It happens that these are the 4 members of Dapper Cracker Brand snack foods. And considering I plan on crushing that competition, we're going to take them out of this study. All right. And now, if you're an actual statistician, which I know many of you will be in the future, you just can't remove data like I just did. But instead, what you would do is sort of inspect, look into it, dig deeper. Why are these points so far off of the rest of the trend? And what you might find is, oh, there was a data entry mistake, or, oh, these people gave biased answers because they have another agenda, which is to bring down my company and, of course, in the meantime, promote their brand. But since I know that those results are biased, I'm going to remove those 4 data points. Now, on to the discussion. So we're actually going to use this example to motivate the conversation. As you recall, whenever we had a scatter plot, which is what this is, a scatter plot, of course, again, it sort of helps us understand how 2 quantitative variables are related to one another. So what we would do is we would try to fit a model to the scatter plot. And of course, it wasn't always necessarily a linear model, but let's just assume that we have data that sort of fits the description and satisfies the conditions for us to build a linear model. And that linear model would, in general, be of the form y hat equals bx plus a. I know this notation is slightly different in your textbook. They use like b sub 1 for the slope and b sub 0 for the y-intercept. It's whatever you want to use is fine. I'm just going to use bx plus a. And let's say this particular set of around 50 points or so has a LSRL that can be fitted to it with the equation y hat equals 0.5x plus 0.1. Of course, y hat is our predicted happiness in CMH, and x is the actual couch potato brand snack food and beverage eaten. I left out the ampersand because I thought it would be funny for you to watch me try to draw it. So let's see. I'm going to copy that over there. All right. All right, that was actually pretty good. It wasn't perfect, but it also wasn't horrible enough to be funny. So that was, for the purposes of this video, worst case scenario. But anyway, that's the situation. Now, what I want you to understand is this is a model of one single sample. Every time we built an LSRL, it was just a model of a sample. So if I went out and redid this survey with 50 new people, no doubt we'd see a similar trend, I'm sure. As you know, this is a great snack food. No doubt we'd see a trend that as you ingest more of this snack foods, your happiness level does go up. But I very highly doubt that with a different group of 50 individuals, we'd get the same exact slope and the same exact y-intercept. So the idea is now, what would the slope be, or the question is, what would the slope be if we were to actually survey the entire population? What would the LSRL's slope be with that entire population's worth of data? And that's really what this inference procedure is centered around. It's centered around trying to understand the true population slope of the true LSRL. Now, you might hear some noise in the background, by the way. I have the lawn in my building is being mowed, and there's also construction going on. So I apologize if you do hear noise. So now, I just want to introduce you to some new notation. This is the actual ideal population LSRL. I want you to understand that even if we had the entire population, the population's LSRL is still not going to be perfect. It's still going to be a model, because it's definitely not the case that every person that eats, let's say, 10 grams of couch potato brand snack food is going to have the same happiness level. That's obviously true in this one sample, and it will most certainly be true in the population. So I don't want you to get the sense that, oh, if we have the entire population, we can predict every outcome perfectly. No, that's not the case. But what we will do is we would get perhaps a better model to better understand the entirety of the population. So anyway, the notation is mu of y. So instead of y hat for the sample LSRL, the population LSRL uses mu of y. I'll explain that in just a moment. The true population slope is beta, and the true population y-intercept is alpha. Now, why mu of y here? Well, this picture is from your textbook, by the way. The idea is that for any, let's say, any gram intake of couch potato brand snack food in the entire population, let's say like this is 5 grams. If we were to take just that slice of people in the entire population and measure their happiness level, the theory goes that the LSRL point would be placed at the average happiness value for that number of grams eaten. Similarly, let's say if we go up to 6 grams and just study this slice of people, the LSRL point would be placed at the average of average happiness level of those people, so on and so forth. And so that's why we use mu y here, because the LSRL is going through the average happiness level for each gram intake. So just a little explanation of the notation. Now, you'll see below here, I have my hypotheses. So if you were going to do a hypothesis test, you would ask the question, is there a relationship between these two variables or not? That is really the major question. Are these variables related? That was supposed to be a question mark. Or in other words, are they associated? Is there any sort of linear association between the two variables? I guess that's really more to the point, so let me actually correct myself. When we're doing a linear regression inference procedure, the question is there a linear association between these two variables? Right, and so that being said, I want you to take a moment and actually think about what the null hypothesis should be and what the alternative hypothesis should be. Notice that the hypotheses are based off of a value for beta, the slope. So think about it. What should we assume about the slope, and what should we try to claim about the slope? So you pause and think about that. Okay, so I'm going to assume that you paused and thought about that. So of course, what we will do, and this is similar to the chi-squared test of independence, what we are going to actually assume is that these variables are not related, or they're independent of one another, or not associated. And so the assumption is going to be that beta is equal to 0. So in other words, if we were to just take the entire population and ask them, you know, how much of the food they've eaten and how happy they are, there's just going to be a complete random scatter around the scatter plot, no discernible pattern at all. But if we're just interested if there's simply any association, we would say beta not equal to 0. However, if the question becomes, is there a positive linear association, you might change that alternative to say, is it the case that beta is greater than 0? That would be the claim that you're testing. All right, and so let's stick with beta greater than 0 just for this situation, because, well, just looking at this sample, pretty clear that there seems to be a positive association. All right, so I'm going to skip the conditions. You could read the textbook, or like I said, the follow-up video by your peers. They do a pretty good job of discussing the conditions that you would have to check. But as far as the test statistic goes, as I mentioned, it's a T distribution. The degrees of freedom are equal to n minus 2. Oops. Sorry. And of course, we are modeling the slope, the sample slope. So as we went, if we went in and chose many different samples, how would our sample slopes be distributed? In this case, we happen to get a slope of 0.5, but if I went in and chose another sample, I might get a sample slope of 0.3 or 0.6 or something along those lines. So there's obviously a distribution of sample slopes. So what we're trying to study is, what is the distribution of these sample slopes? And of course, we are assuming that the true slope is 0, therefore the distribution of sample slopes will be centered at 0. And then, of course, the other parameter would be the standard error of the sample slopes. We pause for one moment. All right, I'm back. A couple of things. I don't know if I said n minus 1, but I definitely meant to say n minus 2, and I definitely meant to write n minus 2. I really hope that I said n minus 2. But anyway, the degrees of freedom for this are n minus 2, n being the sample size. Now, I paused because I wanted to look back at what the standard error formula is for your sample slopes. And this is what the calculation is. S of E is the standard deviation of residuals. And this has its own kind of slightly strange calculation. I'm going to leave it up to you to look it up. It is page 551 in the textbook. And S of X is just simply the standard deviation of the X values in your sample. Alrighty, so there we have it. And then that being said, if we wanted to calculate the test stat, we would take our observed slope, so B from the sample, which in our example is 0.5. We'd subtract what we are assuming about the true slope. In other words, the expected slope, right? This value 0 that we see here is the expected sample slope, because that's what we're assuming is the true population slope. And of course, we would divide by the standard error of B. All right, so that is your test stat and the p-value. I mean, no surprises here. From this point on, like everything else runs exactly the same as any other hypothesis test. So this is probably just gonna be the last thing I tell you. The p-value, of course, would be the probability that you observe a sample that you did happen to observe or greater, based on the assumption that H null is true. So since we observed the sample slope of 0.5, the question will be, what's the probability of observing that sample slope or greater? And of course, in this case, I'm saying or greater than or equal to, because of the fact that my alternative hypothesis in this example is that we are making the claim that the true slope is greater than 0. And there you have it. I mean, that's the idea. The whole thing is that we run hypothesis tests on linear regression based off of a question about, and there's the lawnmower, based on a question about whether or not the two variables are linearly related in some way, maybe positive, maybe negative, maybe just simply related. And of course, if we're trying to answer that question, the natural parameter to inspect is the slope, right? So even if there is no association, the y-intercept would not really tell us that, right? The y-intercept doesn't give us any indication of an association. It is really the slope of the model that tells us whether there is an association, a linear association or not. Alrighty, ladies and gentlemen, there was one last thing that I wanted to mention. Yes, so if you do end up rejecting the null hypothesis, let's say we go about, we run out the full procedure, we reject H null, that means we have found evidence that H null is, the true slope is not equal to 0. And in this particular situation, we would have found evidence that the true slope is greater than 0. The next step that someone trying to study this situation would be to build a confidence interval. And so That's called a linear regression t-interval, and that's actually what your peers do. They do a video on linear regression t-intervals, so I'm going to leave it to them to explain it to you, but that would be the next step. Once you reject the fact that beta is equal to 0, you might want to actually try to estimate what the actual value of beta is by building an interval. And one last thing, you can, of course, do all of this on a calculator. So let me quit out of here. If you press stat, scroll over to tests, and all the way down, you'll see linear regression t-test. There's also linear regression t-int. And all you do need to do is enter the observed sample data into list 1 and list 2. One thing I do want to point out here is, notice they have the beta and this other strange symbol. That strange symbol, which looks like a P, is actually called rho. It's a capital R, let's say, in Greek text, or it stands for the letter R in Greek text. And I'd like you to think for a moment what rho might actually represent. Of course, based on this context, we're talking about linear regression. Remember, one of the important quantities that tells us the strength of linear relationship is the correlation coefficient, or R, right? So rho would be the true population value of R. If we surveyed the entire population and ran a regression, what would the true value of R be? So that's what that is. And essentially, the hypothesis that we stated in terms of the slope can also similarly be stated in terms of correlation coefficient, right? If the slope is positive, then R is positive. If the slope is negative, then R is negative, so on and so forth. So that's why you would see that there. If you want your regression equation, so the sample model pasted into Y1, that's what this is for. And then you would just press calculate and get all of the information that you typically get from any other hypothesis test. All right, folks, so that's all. I want to say again, thanks for being such a great student. It was a really strange year, but you know, I think we made the best of it. And thanks again. And I hope everyone is well over the summer, and I can't wait to see you all next year. Take care.